Right, yes. Today I'd like to talk to you about an independent project done by a calibration consultancy company called Zedeca. It's called the Moon and Earth Radiation Budget Experiment. It's an attempt to improve satellite climate data records to a level where we can finally use them to start resolving which climate models are getting things like cloud simulations correct. This first slide is probably bread and butter to most people in this room. But as I say, the IPCC has stated that pretty much the biggest unknown about these climate models when you run them forward is how they simulate clouds. We're not sure, as we warm the atmosphere from CO2, are we going to get more clouds, less clouds, different clouds? Are they going to accelerate the warming, or are they going to slow it down? Now, I'm sure as most people in this room know, Earth's weather climate system is essentially the work done from a global scale heat engine, where the heat in comes from incoming sunlight or shortwave radiance, mainly around the equator. And the heat out of that engine is, of course, the outgoing infrared or long wave coming from around the planet. Now, in keeping with the motto of this meeting, observations lead the way, we must have global measurements of these fluxes, these shortwave and longwave fluxes, which are components in the Earth radiation budget. However, the 2007 decadal survey said that the biggest issue with measurements such as these is their lack of accuracy. The ability to use them to detect mere decadal scale cloud signals. So around the same time, some of the climate community got together with some of the Earth observation community and they said, okay, these cloud signals, how big are they? And in terms of albedo or reflected shortwave, they said, we think they're about 0.8% per decade. So that's the horizontal green line. Then they said, how good are our measurements, say from MODIS? And they factored in things like natural variability, things like El Nino, the solar cycle, and they came up with an equation that said you would not be able to detect a 0.8% per decade signal till the year 2050. So it would be until then you could say, yep, that cloud signal you predicted is happening. So around the same time, they came up with a mission called CLARIO, which is the Climate Absolute Radiance and Refractory Observatory. They said, let's put some fantastic new instruments up there that are SI traceable. However, because of that natural variability I talked about, you're still not going to be able to detect the signal till nearly 2040, which hopefully will be around the time I'm thinking about retiring. So, got us thinking, how can we do better? Well, to date, there is only one instrument that has measured albedo, solar albedo, to a level that you could use to detect these cloud signals. That instrument was called CWIFS, and it did this by every month pitching over and scanning the moon. Now, Earth radiation budget is a little bit different from measurements you might be familiar with, like those from MODIS. What you do for Earth radiation budget, you've got to measure everything. So the total area under the shortwave spectrum here and the total area under the infrared spectrum on the right. And these measurements have been made by these missions since the 70s in this table here. Now, the most established of which is this series, which stands for the Clouds and Earth Radiant Energy System, on board Terra, Aqua, MPP, and J1. And interestingly, all of these instruments have either regular scans of the moon or regular scans of the sun. And Ceres started scanning the moon regularly in about 2002 to validate its telescope point spread function. So that led to the idea of the Moon and Earth Radiation Budget Experiment, where our target is 0.3% absolute accuracy. And we do this by following a couple of very simple golden rules. First, and most important, different instruments viewing the moon must measure the same lunar albedo and the same lunar thermal output, whether it be the American Ceres devices, the European GERD devices. Secondly, important for the Ceres devices, where we're lucky enough to have two instruments on Terra and Aqua. And so you've got two instruments, then what they're doing is, as you see in this movie, they're constantly up there right now, scanning left, right, left, right. That means about every 3 seconds, they are viewing the same Earth target, not the moon, Earth. So the second golden rule says if you've done your job right, those two instruments should measure the same thing for all Earth scenes, no matter what they are. So let's take a look at number 2 with existing data from the Ceres program using this calibration from 2016. So this is the difference between instrument 2 and instrument 1, the percent difference. And you see it's far from this goal. Sometimes for scenes like clear ocean, they're 1% different. Now this is important because Ceres is assumed to be 0.9% accurate. These mere relative differences are bigger than that. And also because a climate record is only one Ceres instrument operates in climate gathering mode at a time. So if you construct a climate record from Ceres, as it switched between the instruments, between every 3 months they switch from one instrument to the other, you'll get these jumps up. The albedo will go up, down, up, down. So what Murby has done, has used this paper, for an AMS paper from 2009, to put the two instruments on a common radiometric scale. So what you see here is an order of magnitude increase in relative accuracy. So this is shortwave or albedo. This is the series data in the long wave. And this is important because, again, you've got 1% differences. And these are series long wave data is assumed to be 0.5% accurate. You're more than double that. So Murby, again, using this technique, an order of magnitude increase in agreement between the two instruments. So that's Golden Rule 2. Now let's look at Golden Rule 1. So what you see here on the top are the blue diamonds are retrievals of lunar albedo for different phase angles. In the middle here, you've got full moon. On the bottom, you've got retrievals of effective surface lunar temperature. And what we've done is we've defined an SI traceable Murby-Watt scale, which is at 7 degrees positive phase, when the moon kind of looks like this. The black dots on the top that lie on top are the United States Geological Survey Rollo model. This is the model that was compared to CWIS to prove how fantastically stable it was. And you see how nicely they lie on top of each other. In the mold of Rollo, we've come up with a thermal model as well. So in order to normalize to this SI traceable scale, we simply take the blue diamonds and divide them by the black dots. And you see we get about a 13% albedo and about 366 Kelvin temperature. So what happens when we do that? We retrieve from CFM1, Cirrus Flight Model 1 and 2 on Terra, Cirrus Flight Model 3 on Aqua. You stabilize the record. You do a time linear perturbation to the detector gain to force this to be a flat line. And if you do a statistical analysis on this, you'll see the confidence that there is zero trend in this is better than 0.1% per decade. That's 2 sigma. In the infrared, even in the long wave, it's even better because of the high thermal signal of the moon. The confidence in zero trend in this climate data set is better than 0.02 degrees Kelvin per decade. Why why set the albedo about 13 and a temperature of 366? Well, people in here who maybe have used series data may realize it's somewhat problematic. It does have a certain amount of SI traceability in the infrared because they stared at a black body on the ground and they have onboard black bodies in flight. However, that was not the case in the shortwave. In the shortwave, series stared at a light bulb in the calibration lab, and they, let's say, got 100 volts out of the instrument. They then took a separate reference detector and stared at the same light bulb. And that reference detector said, well, that's about a 100-watt light bulb. So you know you get 1 volt per watt of light. However, they never measured, they never characterized this reference detector. It's been sitting in air for decades. That is probably the reason why, across the globe, series measures a net positive input of over 5 watts per meter squared. And that's likely because of this problem. So what we've done, because it has SI traceability in the long wave, we've defined the thermal Murby-Watt based on Terra measurements of the moon. But in the short wave, if you extrapolate your data over the diurnal cycle and fix it to have a global imbalance of about 0.8 watts, which climatologists think is realistic. They think there is a small positive bias, and they think that's the energy being dumped into the deep oceans. So you set it there in the period between 2000 and 2002 at 0.8. And the exciting thing is you now have 0.1% per decade confidence. Any trends you see in this are real, not due to the instrument. Something else you can do, you can take a look at series data that's out there right now being used to validate climate models. And you see that this is data, shortwave data, albedo data from the CFM1 instrument on Terra, which is often dubbed the primary climate instrument. You've got a negative trend of about 1% per decade. That's not to do with the climate. That's purely because incorrect calibration is being used. And that trend is bigger than the 0.2% per decade maximum trend that is generally assumed to be the worst case scenario in terms of this instrument. The trend is even bigger than, remember that green line, the 0.8% per decade? It's bigger than the signal you're looking for. In the infrared, conversely, the trend is positive. And now you've got a trend of about plus 1% per decade. Almost an order of magnitude bigger than the 0.15% per decade trend that is generally assumed to be the worst case. The proof in the pudding, though, finally, is what happens when you plug all this into those Clario equations. Well, because of the fantastic longevity of the series devices built by Northrop Grumman, and because you've effectively gone back in time and fixed data from decades ago, you get this black curve here, which says that if there's a 0.8% per decade trend due to cloud forcing and feedback, you can see it by the end of 2015. People in the audience may know more than me, but I believe that the instruments on Terra could keep operating into the 2020s. If you can keep it going till 2022, you could detect a 0.4% per decade trend. This means you could halve the uncertainty surrounding climate sensitivity to cloud forcing and feedback in less than 10 years. Almost a quarter of a century sooner than would be possible, even if you had, say, a new Clario device. So to summarize, if you use improved calibration on the moon, what you see is series of results being used today to validate and constrain climate models are not as accurate and they're far less stable than is generally assumed. So what MERBI has done is it's completely recalibrated all the American Earth radiation budget measurements dating from the start of the century. And these will be released in about a year in HDF format, and what they'll be is the SSF, single scanner files, so as well as the SI traceable fluxes, you'll have all the latest and best cloud retrievals to go with it. It improves accuracy by at times an order of magnitude over series, based on lunar scans and improved methodologies. And independent results suggest from the Clario team that MERBI is in fact an existing part of a climate observing system, already decades old, bringing the desired capability to begin narrowing the uncertainty surrounding climate sensitivity with the possibility of halving it in less than 10 years. For the 2007 decadal survey, this is what the climate community requested. And by all metrics I'm aware of, it may be what they now have. Thank you for your time.
Any questions?
Just wondering if the absolute uncertainty of the Rollo-Stoller model is important to your uncertainty. So does the kind of division cancel that error out? My understanding is that for the operational calibration, for example, MODIS, they use the Rollo and Moon observations to get the trending in time, but they don't use the absolute calibration because it's only 2 or 3%, for example.
It's probably more like 5 to 10, actually.
Okay.
But yes, I mean, look at it this way: if you wanted to measure the growth of your child, and I gave you a ruler, I don't need to tell you anything about the length of that ruler for you to measure that your child grew 10% last year. She grew 0.1 rulers. So that's why what we've also done is we set the MERBI watt scale to give you realistic climate data. I mean, if you think of, because all you're doing is you're doing the blue diamonds divided by the black dots. So is the moon really 13% albedo? Probably close. If let's say in 10 years we find out the moon is 13.013%, then all you've got to do is divide all the MERBI fluxes by 1.01. It's still, by definition, SI traceable. We don't have, unfortunately, the capabilities to get instruments up there that are SI traceable right now. So this is the best thing we could come up with.
Another question?
Janet Daniels has used the moon series observations, and they show that over a year period, you can get 0.2% accuracy using the moon. Now, the variation of that is because of the libration of the moon. You're going to have that regardless of your instrument, and that is going to limit the accuracy that you can get.
Yes, that is absolutely correct. The Rollo model basically accounts for that, however. So what you've got here is this is what I define as static. That is when the moon is basically, you're an observer above 0 degree latitude and longitude. Now what you see, the blue circles are the observer position on the moon. The yellow diamonds are the sun position. What you are doing is you are using that Rollo model to normalize. An analogy I would give for it is, let's say you had a meter ruler of steel and a meter ruler of lead, or a yard of lead, let's say, and you compared the rulers, but you didn't do it at room temperature. You would need to use thermal expansion coefficients, which are a relative measurement, in order to adjust for the expansion of lead versus steel. That's essentially what the Rollo model is doing. Libration is very important, however, but you have, from each instrument, you have about 2,000 independent measurements. So what you get is, that's why the confidence intervals are so low, because you've got thousands of measurements. So the accuracy of the roller model is in fact actually not that important.